Hi there guys, this is 12H. Up until now we've worked out exact solutions to coupled linear differential equations, and now we're talking about working out approximate solutions to coupled differential equations which are linear. Okay, and in fact we've done this before. We did this at the end of chapter 11, I think it was, and that was when we used Euler's method, and that was in terms of x and y. So now we've got this extra parameter which is also changing, which is t. So we have this with respect to time as well. So previously we were looking at just xy graphs, and if you remember, it developed on from slope fields to then say, well, if we can work out the gradient at any particular point, then we can move on to the next point using Euler's method. Now we have here x and y both being dependent on t, so we're going to need to adjust Euler's method here to say we've got x, have a little look down here, we've got x plus this extra amount of t times by essentially our gradient for dx dt. That's what this thing is going to be here. Now, let's go back to Euler's method just to recap on that, to talk about, how that practically worked. So a bit of theory there. And then let's look at the particular example here as well. Now, it's worth noting that this is almost the last thing in the formula booklet. So I'm going to take it from here. So we had Euler's method here, and then we had Euler's method for coupled systems, which is what we're dealing with now. So it's just going to be this. In fact, this is really not that difficult. It's just number crunching and being able to use your calculator. So let's have a little look. So I just copied this one across. So previously, again, we were talking about XY coordinate systems. Let's come up with an XY axis here. And we came up with our slope fields. And so we can say that at any particular chosen XY coordinate point, we can get to the next one by considering, say, for example, the gradient at this point. If you remember, we put on a little gradient line there for the slope field. So if that's our coordinate point, we could put a gradient line on there. And we could use that gradient and say, well, okay, if I want to go across to the next one, so a little bit more on top of x here, so we're going up, say, by 0.1 or by 1, and then we say, to get to that next place, to get to the next point, we're going to use this line, follow that one up. So we go 1 across, or 0.1 across in x, whatever that value of h is there, h here. And to find the new value of y, we need to times the gradient by the x value. Okay, so that's what we're doing here. So the x value is essentially the height, the change in height. So that's this amount here. That's the change in x essentially. So times this value by the gradient, and it will give us the increase in height. So that's what we're going to need to add on. Okay, so I mean, practically, if we had, was a bit, say for example, this was the coordinate point, I don't know, 2, 3, and say for example the gradient was, I don't know, the gradient was 2, and if we choose to have a step of 1, then if we do 1 times 2, we're going to be 2 further up here. So that's how far we're going to go up to the next y coordinate point. So the next point would be at 3, because I added the 1 onto the x value, and then plus the 2 on, which would be 2 times by the 1 here. Okay, that would be the 1 there, and that would be 2 there as the gradient. Okay, so then we would be adding on the 2, so that would take us to 5. That would be our next point. And at the next point, we work out the gradient there. Maybe it's like this, and then we go on to the next point, and so on. Work out the next gradient and move up to the next point, and so on. Okay, so that's what Euler's method was all about. And here, the only difference is we're now doing, essentially, we're finding x based on time. So it's the same formula you see as this one here, except for x is dependent on this time. We want to know what the xy coordinate point is at a particular time t. So again, we're going to say, well, let's take the x value where we were before, so not the y value now. The x now becomes our height, if you like. And then h is still your step amount across to the next point. So that will be your change in t, in fact, which is shown through this bit here, whereas previously h was your change in x. And we're going to find the new height, if you like, so the new x value, by doing the original x value and then timesing by your gradient, essentially at that point, by your step value here, and or your step length, and it will take you up to the next point. So it's the same thing, apart from we're now dealing with x and t, whereas previously we were dealing with y and x. So x essentially becomes your dependent variable. Now this thing here is really your dx dt. Okay, and it's the dx dt at this point here. So this might be, for example, the coordinate point, I don't know, t n x n, and the next point would be t n plus 1 and x n plus 1. Okay, so when we're finding x n x plus 1, we're using the gradient at this point here, take us to the next point up to here. Okay. Now, of course, the graph would really be a curve in most situations. It's not going to be these chunks of straight line. And that's why it's an approximation to where the next point is going to end up. Okay, so this is dx dt, and dx dt, the reason why they have these things inside the brackets is because they're saying this is dependent on x, y, and t. So the gradient essentially depends on time, but actually the gradient also depends on x and y. And that was obviously how we set up these coupled linear differential equations. We said, you know, maybe dx dt depended on x. So maybe we could say 2x plus, I don't know, 2x plus y, for example. And that's how we set these things up in the first place. So now, obviously, the gradient is going to depend on both the time, but also on the x value and the y value, the previous one here as well. Okay, hopefully that's making a bit of sense there. And obviously, this is essentially a corrupted version of this, where x is now our new dependent variable. But we can do this for y as well. So we can also say, well, y also depends on time. But also, the gradient depends on x, y, and the time that we're given. So there you go. So that's just, again, a slightly different version of this one. And then, of course, t is just, well, that's our time increasing by certain step lengths which we choose. Now, often the step length is chosen to be 0.1, but it could be something else, of course. Okay, now this would take a long time to do if you're trying to find these approximations. So you're getting your x values over time. You know, so x is changing over time, and of course y is changing over time as well. So there's a graph there, and that would take you ages to find all of these without technology. So we've got to do it with technology. Now, just before we do this example, let's just have a look at a little bit more what they say in the book, because they just talk about some context here. They say many ecosystems contain species that are closely connected, often competing for limited resources. It is possible to find population sizes where both species can exist together, or will one, is it possible rather, or will one always come to dominate the other over time? Now, that's where we're going with the next exercise. So we're going to put this in context in the next exercise, and it's going to look at predator-prey models. That's really kind of interesting real-life applications of all of this. But at the moment, we need to look at the approximate solution to coupled linear equations. Okay, so let's apply this thing then. And this one says, use Euler's method, or use the Euler method with a step of 0.1 to find the approximate values of x and y. We've got when t is 1 and t is 2, and it gives us some starting conditions here, and x dots, dx dt and dy dt there as well. So we've got starting initial conditions when time is 0, but x is 4 and y is -2. Okay, so this would obviously take ages if we were going to do this without technology. Now, I'm going to show it with Excel, but then I'm going to talk afterwards about the calculator version, which you're going to need to look at as well. So look at this in terms of Excel. And I've already started setting this one up. Here's the initial condition when t is 0, x is 4, y is -2. And then here's my step value here. So I'm going up in 0.1s. And now looking at the formulas, look at the formulas, we've got x n plus 1. So the next value of x is xn plus h, which is going to be 0.1. So the previous value of x times by, and this is dx dt. Okay, so let's look at the question. What's dx dt? That's 3x minus 4y. Okay, so going to Excel then, you can see that I've done this one here, so the previous x value, that's C4, plus the step length, which is 0.1, so it's this thing here, and then times by, and this is dx dt in here, that's 3 lots of x, subtract 4 lots, so you can see in here, subtract 4 lots of y. Okay, so that's how I'm setting this one up. Now, when I move on to the next square, it will just take all of those values from the previous square. So obviously, if I copy that one down, now my C4s become C5s, for example. Okay, so it just depends on the previous line. Okay, now for y, let's have a look at this one from the book as well. For y, they had dy dt was x minus 2y. So x minus 2y was dy dt, that was x was C4 minus 2 lots of y, that was in here, the blue cell. Still got the same step length there of 0.1. And I'm adding this on to the previous y value because this is how y is changing given this gradient, if you like here, dy dt. Okay, so that's how y is changing over time. Now, pretty straightforward here to copy this. Let's just zoom out a little bit here. So let's just copy this down. Let's take it up to 2. I can see that's 2 there. And I'm going to copy these formulas here. I'm going to go to the little black plus in the corner. When I hover over it, I'm just going to copy all of those things down. Let's zoom in a little bit here as well. Okay, so we're getting here values at the end for x is 306, and value for y when t is 2 is 76. So let's just check that with the book. And we can see, there we go, when t is 2, we've got 306 and 76.2 there as well. Okay, so that's pretty straightforward with Excel, of course. But they obviously do this with the calculator, and you're going to need to do it with the calculator as well. So let's just talk through the calculator version here. Now, you will see that when they have set this up, when I set this whole thing up here, I come up with formulas which could have been simplified. So we had C4 in there and 0.1 times 3 lots of C4. Okay, so that gives us 1.3 lots of C4. And also plus, minus 0.1 times 4, so 0.4 lots of D4. So ultimately that could have been simplified, and that's what they've done in the first instance in the working out here. They've said, sure, here's the formula, but let's simplify this into this thing here. Now, you don't need to do that. If you just want to type this straight into your calculator, you can do, no problem. But they've simplified it here, and that's what they've used in the calculator example there. So you will not see this, you will see this version here. It's just a simplified version of this. Likewise, they've done that with y as well. Okay, so let's check out how they've done it with the calculator. And this is the TI Inspire, of course, this version. And we've done this before, but again, it's really good to follow this one through. So if you go to new document in graphs and add a graphs page, and then you go to graph entry or edit, so menu 3, and then you go to sequences, and then you go to sequence 1, and then you can put in this first equation, or potentially you can put in the T1 if you want. I think actually I might put in the T1 to start off with, because essentially that's what I did here. But they're putting in X first. So you can see what they're doing. I'll just go through this sort of slowly here so you can pause the video if you need to. So they're putting in this formula to start off with. they're saying, well, let's put it in as U1. That's the option that the TI and Inspire will give you. And then U1 is just the first sequence. And then you're going to set it up like this. And we're going to say we've got 1.3 lots of the previous X value. So that's UN minus 1. Okay, so they're not using UN plus 1 and UN minus and UN. They're using UN and UN minus 1. So that looks a bit different there. And then take away 0.4 lots of the previous U2, the Y value. Okay, well, we haven't actually defined U2 yet, but don't worry about that. We'll do that next. And they're saying here that we're going to have an initial term of 4 for the X value, and we're going to have steps of 1, not steps of 0.1. So we're going to go up in ones here. Okay, so we're going to go up in ones, but we have already incorporated the 0.1 into the formula. If you look at the formula here, that was the 0.1. That's the step value here. Now we're going up in ones there in terms of the terms, the step number of the term. We're saying, well, we want the first term, the second term, the third term, and so on. So it's just saying, well, look, this is the first term, the second term, the third term. Now I might call that X0, but they're calling it the first term, X1, if you like, or they're calling that for the sequence U1. This is when n is equal to 1. Oh, okay, right. So that's how they're setting this one up, of course. So then they're saying when X is 4 is the initial term, and then the step number is going to be going up in ones. Okay, so that's sorted. Now, step is going to be going up in ones there as well, and we can put U2 in an exactly sort of similar way, and that's going to be dependent on U1 and U2. And then we're going to do U3, so we're going to put T in as well, and this is going to be useful just in the table to know what the time value is. So basically, neither of these depended on U3, so that's fine. And we defined that we were going up in 0.1, so it kind of was dependent on time. It was dependent on how much the time increment increased each time. However, having this third one here is going to be really helpful for us to know when we're finishing. Okay, so if we just look down at this, we'll see that having the time value here, we can see, but here's our values when time is 1 for X and for Y. So although this is not necessary, it's actually really useful to have in there as well. So that's easy. Again, we can put in another entry line here. Tab, display the entry line again. This time we're going to come up with a new sequence here. And so we're setting up this new sequence. And this one is pretty straightforward. We're saying the previous one plus 0.1. Let's start at 0 for the time, and let's go up in ones. Okay, so press enter when you're finished, and then you're going to need to then go document and add a page, control document, add a page, and then we're going to add lists and spreadsheets. Okay, so press Control T to change from a spreadsheet to a table, and then press enter to select U1. Okay, so we're going to put U1 in here in this table. So Control T brought us to a table. We'll put U1 in here. Ignore the error messages. Fair enough. And then it says move to the next column, of course. So move further down, move to the next column and press enter U2. Okay, so we're going to put U1 in there, and I think we're going to put U2 in there, U3 in there, basically. Okay, so move to the next column, and that's in here, and then put in U2 and so on. Okay, so scroll down the table using this. It should all be in there now. So you've gone to your spreadsheet and put in U1, U2, and U3, and then you've gone back to your the spreadsheet essentially, and you put in U1, U2, U3. That should be in there now. Okay, so we've just defined 1, 2, 3. I think we've defined these columns. Okay, so now you can just scroll down and you'll find that in the 11th cell down, because we started at t is 0, we need 10 more increases of 0.1, which will take us to the 11th cell that will have our x and y values there. And of course, we'll scroll down to the last ones and we'll find our x and y values there. Okay, please make sure that you do this. Make sure that you can do this on your calculator. Okay, that's pretty much it for this exercise, but there's just one last little bit at the end. And they say here, in example 5, so way back, so 10 pages before or so, it says we had the exact solution to this system of differential equations, and we found it. So find the percentage error in your answers. So you'll need to check back to that, and you'll see that the exact solutions were these for when t is 1 and when t is 2. So we got those ones out. And the percentage errors, it's obviously really easy to do. You can say that the percentage error for x is going to be this 57.6, take away 48.1. So that's the actual error, and divide by the exact amount. So divided by the 56.0. We can obviously take the magnitude of that, so we don't need any negative answers there. And obviously times by 100, that gives you your x error and your y error. And of course, we can do that for time is t is 2 there as well. Okay, now you can see that those errors are becoming really quite bad towards the end there. And in fact, before the exercise even, it did actually say, though easy to apply, I hope you find these easy, that the Euler method is not much used in practice due to its inaccuracies. Other methods include the improved Euler method and the Runge-Kutta method, but these are not in the higher level course. So this is not a particularly accurate method. And of course, if you had a question like this in an exam, you would comment on the percentage error to talk about its accuracy. Okay, so there's 12H. Good luck with the practice there. There's only 3 questions before we move on to predator-prey models in 12I. So good luck with the questions, and hope to see you back for the next one.